Hi, calculus students. One of you asked today how we know whether to use one or two integrals or one or two regions when we set these up. And I didn't get a chance to answer that in class, so I thought I'd do that now. So whether we're doing a volume of revolution with the washer method or just area, let's suppose this is our region here, and we're going to revolve around the x-axis. The difference is that it depends on how many different functions you have defining either your top or bottom of the region. So this one has a dividing line right about here. Let's call that C. So if we're going to define this region, this could be region 1 and region 2 over here. So region 1 would equal the set of all x, y, and x goes from A to C. And then y goes from 0 up to the upper boundary of f of x, right there. So that's the first region, and the second region would be the set of all x, y pairs where x goes from C to B. The y value then again goes from 0 to the upper function of g of x. Okay, so this upper bound here is used for the first region, and the other upper bound on the left side, that's used for the first region. So we need two regions to describe it, and then our area. So the overall region would be the union of these two regions. And when you convert that to an integral, the area would be the integral from, sorry, I have this wrong here. This should be a less than or equal to x less than or equal to c. The area from a to c of f of x dx. Union, we add together the two areas, plus the integral from c to b of g of x dx. Okay, so the key was that we had two different tops to that one. Now, if we had you can ask yourself, what if we had the same region described here and we were going to integrate with respect to y? If we were going around the integrating with respect to y first, how many regions would we need? Think about that for a second. Okay, I filled a little bit more in. And again, this is going to depend on how many different ways we have a lower and upper bound. So now we're integrating with respect to y. And we can see that any y that's from here to here, let's put a c there, has the same lower bound as it does upper bound. Then between approximately across here, that would be my, let's say, my d, and then this top bound up here would be my last upper bound. Let's call that maybe m. Okay, so my first region is going to go from x equals a up to x equals b. That's my lower bound and my upper bound. So my area would equal y goes from 0 to c, and then when I subtract my two x values, it would be b minus a dx. My next one, y goes from c to d, and in that region, I'm going from a lower bound of x equals p of y up to an upper bound of x equals b. So my difference in my x values is b minus p of y. upper bound minus lower bound. In the first one, my upper bound was b, and my lower bound was a. In my last one, think about that for a second. My upper bound as a function of y, and my lower bound as a function of y. Y goes from d to m. Upper bound, I'm sure you got it, s of y minus lower bound p of y. I didn't write out the three regions. We could have done R3, R2, R1, and we could have written three different set notations for my entire region. And each one of these regions would have had its own integral for finding area. Similarly, if we did volumes of revolution around the y-axis, like the Washer method or something, we would have just had these as our upper lower bounds would have been the radii for the Washer method. Hope that was helpful.